Hey Vanguards, I'm here to talk to you today about the sophisticated stoichiometry problems. But first, things that you really ought to know about the periodic table. So make sure you know everything on here regardless of whether it's going to be on a test or whatever. Over here we have the metals on this side of the stair step. Aluminum's obviously a metal, so that's where you start your stair step. These other things are non-metals. Metals, if they're sitting there just on their own, they have a charge of 0. Like Fe, iron, with a charge of 0, cobalt, nickel. If these things get bonded, they'll tend to throw away electrons. Electrons have a negative charge. Throw away negatives, what's left behind is positive, cations. How do you remember that? Calcium is over here, Ca. We spell cation Ca plus ion, so they get a plus charge. That's how you remember that. So anions form over here, things that get a -1 charge, -2 charge, like oxygen, sulfur, selenium, -3 charge or 3- charge, or minus charge with nitrogen, phosphorus, and these guys in this column here. All right. Another thing that you want to know is this is the 1A column. When you're reading your solubility table, it talks about 1A's, lithium, sodium, potassium, rubidium, cesium. Any of those things that are bonded to something like lithium oxide or lithium fluoride or lithium chloride, these things make compounds aqueous. They dissolve in water, and so you can see through them, just like this copper sulfate solution is aqueous. You can see through it, even if it does have a color. Okay, other things. These in the first column have 1 valence electron. These in the second column have 2 valence electrons. These guys will throw away 1, throw away 2, get a +1, get a +2. The ones in the middle, lots of them tend to get a +2 charge because they all have, it's 1s2, 2s2, 2p6. For example, 4s2 and then 3d1, 3d2, 3d3, 3d4, but they all had a 4s2, so lots of them tend to throw away 2 electrons, get a +2 charge. But there are many, many exceptions to that, and that's an interesting topic for another day. A couple that you ought to be aware of, zinc and silver. Zinc, if it gets a charge, if it's just sitting there as a solid, zinc solid has a charge of 0. But if it's bonded to something, zinc always gets a +2 charge. Silver always gets a +1 charge. So you don't call it zinc 2 or silver 1 because everybody knows what their charges are. All the rest of these in the middle, the transition elements is what that says. The transition elements, which is mostly the D block, but a couple of these get thrown in there too. The transition elements, you always have to use Roman numerals. So for example, iron can be a +2 or a +3 pretty regularly. So you call it F iron 2. Each atom has a +2 charge. Iron 3. Each atom has a +3 charge. And then you might have to crisscross applesauce to get things together. Another thing, this is the lucky 7. They're not really called the lucky 7, they're called the diatomic molecules. In other words, anytime N or O or F or Cl or Br or I or H, anytime they're by themselves, all alone, like in a test tube or something, they form pairs. So then you get N2O2, F2, Cl2, Br2, I2, and or H2. The noble gases at the end here, they don't react with anything. Once in a while they will. Xenon, for example, is actually fairly reactive. We're going to do our first problem, and it's going to involve aluminum. When you look at aluminum, it has 13 protons, 13 electrons, 2 in the first shell, 8 in the second shell, 3 in the third shell. So if it's just aluminum with it's a metal, it's shiny, conducts electricity, it's got a charge of 0, but if it bonds to something, aluminum will throw away 1 electron, 2 electrons, 3 electrons, get a +3 charge, Al +3. So you might have aluminum bonded, I know this is review, you might have aluminum bonded to, say, fluoride, F. It gets a -1 charge. So +3 - 1, crisscross applesauce, AlF3 is the compound. A tricky one is aluminum oxide. Al is from the left, O is from the right. Ionic. Al gets a +3. O gets a let's see, it throws away gains 2 electrons, gets a -2. So crisscross applesauce, Al2, O3. So aluminum oxide, and notice I don't have to say aluminum 3 oxide because it always gets a +3 because it's not a transition element. So its formula is Al2O3. If you have aluminum bonded to some sort of polyatomic ion, let's say aluminum and hydroxide, you have to memorize hydroxide has a -1 charge, -1. Aluminum gets a +1, +2, +3. Crisscross applesauce. The formula is AlOH3, aluminum hydroxide. If you have aluminum bonded to, say, phosphate, Al gets a +3. Phosphate from your flashcards, PO4 has a -3. Plus 3 minus 3. Aluminum has a plus 3 charge. Phosphate has a minus 3 charge. Plus 3 minus 3. It's a 1-to-1 ratio, so one of each of them. So you can just get rid of the 3's up there, AlPO4. So aluminum has 13 protons. It has 26.98, let's call it 27. 27 minus 13 is 14 neutrons in the nucleus. I've weighed out 1 mole of aluminum. Weighs 27 grams. 26.98, I set this to 27. So 27 grams, that's 1 mole. There's 6.02 times 10 to the 23rd molecules. The first problem we're going to do, I think, talks about 6 moles of aluminum. 6 moles. 6 times as much. So this is some more sophisticated stoichiometry problems. Balance the following equations and then find the desired quantity or quantities. Only calculate the required quantities. So, in other words, you're going to be making these lines underneath here, each one. In most problems, you do not have a number for every one of these blanks. In most problems, I'll just say, all right, given you have so much of this copper sulfate, how much copper will you make or something? And you only have to do those 2 parts. So keep your eyes open. If you're confused, you can do everything here and then just at the end pick out your, the answers, but that takes a lot of extra work and I don't see the point in doing that. So it says, if 6 moles, 6.0 moles of aluminum is used in the following reaction, how many moles of copper will be formed? So I'm asking you about this column underneath aluminum and this column underneath copper. The first thing you have to do is get the proper skeleton equation. This is done for you. This is copper 2 sulfate. I put a parenthesis around this to indicate, to remind you that sulfate is one thing, it sticks together. And it makes aluminum plus aluminum sulfate plus copper. You have to balance the reaction first. Make sure you balance it. 1 copper, 1 copper, 1 sulfate, 3 sulfates. Uh-oh, I need a 3 in front of this, which means I need 3 Cus as well. So this is good. 1 aluminum, 2 aluminums. I need a 2 here, and we're good. It's a 3 to 2 to 1 to 3 mole to mole to mole to mole ratio. Let's see, we are talking about how many, let's see, this column and this column. That's all I need to do. So I'm going to put a line, line, line under this, and line, line, line under that. There are 3 quantities that you need underneath each species. Underneath this species, underneath that species. When we start to talk about gases, we'll actually add a 4th line underneath this. The calculator that we used said that moles equals grams divided by molar mass. If you've forgotten, let's say you wanted to calculate moles. You cover up moles, and that would be grams divided by molar mass. If you had to get molar mass, you cover up molar mass, and it's grams divided by moles. If you want to get grams, cover up grams, moles times molar mass. That's how that works. Every equation, you start off with some number. In this case, I just randomly chose 6 moles of aluminum. So, like I just told you, this is 1 mole of aluminum right here. A mole, lots of times, is like a handful of stuff, right? So that's 27 grams. 6 moles of aluminum, all right? How many moles of copper? All right. So we have a 2 to 3 mole to mole ratio. So 2 is to 3 as 6 moles is to how many moles? Maybe you can do this in your head. The answer is 9. 2 is to 3 as 6 is to 9. Let's say that that's not coming easily to you. You can set up a proportion. Can I use this little space right here to show you the proportion? I know this is in the middle of the screen. You would say 2 is to 3 moles as, equal sign, 6 is to x, because this is our x right here. The question asks how many moles of copper? 2 is to 3 as 6 is to x. Now if you're going to solve this in algebra class, you'd cross multiply 2x equals 6 times 3, which is 18, and then you divide by each side by 2, and that gives you 9. And let's see, we're supposed to have 2 sig figs, so I think it's 9.0 moles. That problem is done. You didn't have to do anything underneath copper 2 sulfate. You didn't even have to do the grams or the molar mass here. You didn't have to do that here either. This problem was super easy. Oh, we're not done. What kind of reaction was this? Double replacement, single replacement, combustion? Well, let's see. We had a cation and an anion, and then along comes another metal and says like, hey, let me dance here. Does aluminum actually beat copper? I need my activity series for this. Let me see, it's in the middle right here. There's aluminum and there's copper. Aluminum wins. It's more like Larry lithium. Yeah, so this reaction would occur. We would get 9 moles. And this is a single replacement reaction. 3 moles of hydrogen gas will form how many moles of ammonia via a combination reaction? Will form, that's the arrow, that's the yield sign, ammonia. So this is obviously ammonia. And 3 moles of hydrogen gas, so that means you take hydrogen, that's one of the lucky 7, right? One of these, hydrogen by itself. So hydrogen is actually H2. And this ammonia has N's and H's. Oh, so what would be over here? It's got to be N, right? Wait, is N one of the lucky 7? Sure is. Take a look. It's N2. So that's our skeleton reaction. Let us balance it. 2 H's, 3 H's. Uh-oh. Sets of 2, sets of 3. How many sets of 2 equal how many sets of 3? 3 sets of 2 give us 2 sets of 3. It's a 3 to 1 to 2 mole to mole ratio if you want to. Write a 1 there, that's fine. Let's see what the question says. 3 moles of hydrogen gas. All right, so 3, right in green here, 3.0 moles will form how many moles of ammonia? Well, I don't need these right now. The question doesn't ask me anything at all about nitrogen gas, so I don't need to do those. It does talk about ammonia, so line, line, line. But the question says how many moles of ammonia will form. We have a 3 to 2 mole to mole ratio. 3 is to 2 as 3 is to X. It's really that simple. 12.0 grams of sodium hydroxide are formed. How many grams of water were used? Well, this question is talking about this species and this species. Regardless, we have to set up the equation and balance the whole darn thing. 1 sodium, 1 sodium. 1 hydrogen, 2 hydrogens. I need a 2 here. 2 OHs, 2 hydroxides. Well, there's my OHs, so I need 2 of them. I need a 2 there. Oh, darn it, I just messed up my NAs, my sodiums. I have 2 on this side, so I need 2 here. It's a 2 to 2 to 2 to 1 mole to mole to mole to mole ratio. 12 grams of sodium hydroxide are formed. There it is. 12.0 grams are formed. How many grams of water were used? Temptation. Ooh, you'd say it's a 2 to 2 ratio. That's the same. 12 grams to 12 grams. But this is a mole to mole ratio. And this number, this is grams. Do not just say, oh, it's 12. That would be wrong. Don't do that, whatever you do. We have to get the moles of these. So if I can get the moles of this, it's going to be the same number of moles over here. My equation is going to be grams divided by molar mass. So I've got grams, 12. I need the molar mass of NaOH. Na is, let me look, 23. O is 16. H is 1. So 23 plus 16 plus 1 is 40, I think. 40 grams per mole. I'm going to write that in black. 40 grams per mole. I have to solve for moles. Grams divided by molar mass. What was I thinking? Shame on me doing these problems without a calculator and a periodic table. Grams, 12.0 divided by 40. Answer is 0.3. We're looking for how many grams of water. So let's figure out how many moles. It's a 2 to 2 mole to mole ratio. I'm not looking at this one. I'm not looking at this one. 2 is to 2 as 0.3 is to X. Cross multiply, or just use my common sense. That's 0.3, 0.3 moles. How do I calculate the grams of this? Grams equals moles times molar mass. I need the molar mass of water. 1 plus 16 plus 1 is 18. 5.4 grams. There's my answer. Answer, write it down here, jerks. 5.4 grams. What kind of reaction? We had a metal and hydrogen acting as a metal because it's written first. Dancing with OH. Sodium comes in and says, like, hey, on my way, buddy. I should have looked this up right off the bat, shouldn't I? Is sodium strong enough to kick hydrogen when it's part of water? To kick it out? Let me look right here. Well, gosh. Sodium is almost as good looking as Larry lithium, so yeah, this reaction would occur. Sodium would kick hydrogen out of the way and become bonded, pour hydrogen out on its own, all by itself, and it's a diatomic gas. It's a single replacement reaction. Let's do number 4. How many grams of bromine gas would be generated along with 16 grams of salt? This is what I'm looking for right there. Generated along with 16 grams of salt. Salt is usually sodium chloride, NaCl. So we have 16 grams of salt. All right.
Let me balance it. 2 Cls, 2 Cls, 1 Na, 2 Nas. Oh, I need a 2 here. 2 Brs, 2 Brs. It's good. We're at a 1 to 2 to 2 to 1 mole ratio.
I don't have to bother with anything over here. And I'm going to focus on this side over here. I need to get the grams of this. So what I'm going to do is I'm going to go from grams to moles, and then moles to moles using my 2 to 1 ratio, and then I'm going to calculate the grams of this. Grams, it's getting kind of messy, isn't it? And then here's moles. It's always been a downfall of mine. I'm kind of a messy guy. Molar mass. NaCl, do not use the 2 when you're calculating molar mass. It's 23 plus 35 is 58. Br, let me look, it's way over here, and it's Br2, so that's 160 grams per mole for that. Alright, calculate the moles, have half as many moles, calculate the grams, we're done.
2 is to 1 as 0.28 is to 0.14. Let me just double check my math. 2 is to 1 mole to mole as 0.28 is to
X. 0.28 is to X. Cross multiply, got her. Let's calculate the grams. Cover up grams. It's moles times molar mass. 0.14. 0.14 times 160. 22.4. 22.4 grams. There's my answer. 22.4 grams. What kind of reaction was this? It's actually, this is kind of a weird one because usually it's metals fighting with metals. In this case, it's chlorine fighting with bromine. Those are 2 nonmetals, but it's still a single replacement SR reaction. Alright, next problem.
Using a single replacement reaction in which solid copper is reacted with aqueous silver nitrate, solid copper, that's Cu, is reacted with, that's a plus, aqueous silver nitrate, Ag, that gets a +1, flashcards, nitrate, NO3, -1, flashcards, AQ, aqueous. And you're going to make some silver. If you want to make 150 grams of silver, Ag, that's silver. How many grams of copper would you need? What other product is formed and how much of it would there be? Hint, copper loses 2 electrons. So copper is sitting here with a charge of 0. Copper is going to fight with silver, like Larry lithium going at it with whoever. Copper is more active. And double check. Yep, copper, silver. Silver is not reactive. And so that means copper is going to lose 2 electrons and bond to nitrate, NO3. Well, if copper loses 2 electrons, it'll get a +2 charge. Nitrate, flashcards, -1, crisscross applesauce. We need 2 of those. Put it in parentheses. Let's balance it. You can't do any stoichiometry unless you balance it.
1 copper, 1 copper, 1 silver, 1 silver. 1 nitrate is 1 thing. Now nitrate over here, we have 2 of them. So I need a 2 of these. Where can I put my 2? I can only put it right there. It's coefficient. So we have 2 AgNO3s. I just wrecked my Ags, my silvers. 2 Ag, 2 Ag. We have a 1 to 2 to 2 to 1 mole to mole to mole to mole ratio.
150 grams. That's what I want to make. How many grams of copper would I need? Well, it would be great if this was a 2 to 1 gram to gram ratio, but it's not. It's 2 to 1 mole to mole. So I need to calculate the moles of silver, and then I'll know I have half as many moles of copper.
To calculate the moles here, I do have to remember my little calculator deal. Moles, grams, molar mass.
Moles equals grams divided by molar mass. I got grams. I need the grams per mole, which is my molar mass. It's silver. Don't use the 2. Do not use that 2 for molar mass. Look up Ag. It's 107.9, I think. 108 grams per mole. I need to calculate my moles. Cover it up. Grams divided by molar mass. 150 divided by 108. It's going to be a little bit shy of 1.5, right? 1.4 moles. We're using 2 sig figs here, right? 150 has 2 sig figs. 2 to 1 mole to mole ratio. 2 is to 1, as 108 is to, let's see, what's half of 108? It's 54, I think, right? 2 is to 1 as 1.4 is to half of 1.4. 2 is to 1 as 1.4 is to x. Solve for that. The question says how many grams of copper. To get grams, I need moles times molar mass. Copper's molar mass is 64, I think, grams per mole. But there's a couple other questions that I threw in here just because I'm mean. What other product is formed? Oh, we got it. It's copper nitrate. All right. So circle it, I guess. And how much of it would there be? How much of it would there be? So that implies how many grams of copper nitrate. So we have to do this whole problem again. Let me hide that down there. All right. So that means we need this, and this, and this, and we need to figure out the grams of copper 2 nitrate. Copper gets a +2, it's in the middle, call it copper 2. NO3 is nitrate. Well, we have a 2 mole to 1 mole ratio. 2 is to 1 is 1.4 is to 0.70 moles again. And the molar mass of copper 2 nitrate is 188 grams per mole. I should use my calculator. Now we need to solve for grams. In grams, let me cover it up. Moles times molar mass, 188 times 0.7. You do that. It's something like 140.